In Module 2, you learn about IP addressing using the transport layer of the TCP/IP framework. Next, we talk about the application layer, HTTP, and DNS protocol. You learn about the OSI model and how firewalls and intrusion detection and prevention systems can help protect your network and data. Finally, you become familiar with the concepts around clustering and high availability systems. Are you ready to learn new networking skills?
In this video, you will learn to convert numbers between binary, octal, decimal, and hexadecimal number systems, base 2, 8, 10, and 16 respectively. This lesson is being presented by Ben Briggs and is based upon a lecture series developed by Moises Mong. Let's talk about networking fundamentals, specifically IP addressing. This lesson will cover the basics of IPv4 addressing and touch on IPv6. I'm sure you've all been exposed to base 2 or binary numbers in school, but I'll give you a quick overview since that was a long time ago for some of us. We're used to thinking, talking, and calculating in base 10 or decimal number system. Humans adopted the base 10 number system most likely because we have 10 fingers and 10 toes, so it's easy to speculate that early counting was done on our ancestors' fingers. Computers, however, only know two different states, on and off, or high voltage, low voltage, or open gate, closed gate, which we represent logically as 1 or 0. Computers can only differentiate between these two states, so this is how the decimal system works. We have digits for ones, tens, and hundreds, thousands, 10,000s, etc., each digit being worth 10 times as much as the preceding digit. Each digit can hold 10 different values ranging from 0 to 9. Remember that the word decimal means 10. In the binary system, on the other hand, each digit or placeholder holds a different value. There are placeholders for 1s, 2s, 4s, 8s, 16s, etc. Each digit being worth 2 times as much as the preceding digit. In binary, each digit can hold only 2 different values, 0 or 1. Remember that binary means 2. So converting from binary to decimal is easy. Just add up all the values of the digits that contain a 1 and ignore those that contain zeros. In this example, we have an 8-digit binary number, so there are 8 placeholders. So the decimal equivalent of this number would be 2 plus 8 plus 16 plus 64 plus 128, or 218. Converting from decimal to binary is a little more awkward, and it might remind you of the long division you learned in grade school. Of course, there are plenty of calculators and online tools that will make these conversions for you, but here's how it's done. In this example, we have to convert 235 from decimal to binary. Start by seeing what is the largest binary placeholder you can subtract from your decimal number. 256 is too large, but you can subtract the next smaller placeholder, 128. So put a 1 in the 128 place, and then subtract 128 from 235, and you're left with 107. Check to see that you can subtract 64 from 107. Yes, you can. So add 1 to the 64 place, and then subtract 64 from 127, and you're left with 43. Checking the next placeholder down, can we subtract 32 from 43? Yes, we can. So we add 1 to the 32 placeholder and subtract it from 43, leaving us with 11. Check the next placeholder down. Can we subtract 16 from 11? No, we cannot. So we put a 0 in the 16 place and check the next placeholder down. Can we subtract 8 from 11? Yes, we can. So put a 1 in the 8 placeholder and subtract 8 from 11 to leave you with 3. As before, check the next placeholder down. Can we subtract 4 from 3? No, so we put a 0 in the 4 placeholder and check the next placeholder down. We can subtract 2 from 3, so we add a 1 to the 2 placeholder and do the subtraction. Now we have 1 left, and the next placeholder down is the last one, 1. We can subtract 1 from 1, so we put a 1 in the placeholder and do the subtraction. 1 minus 1 is 0, so we are done. So this will be the representation of 235 in binary. 111011011. So that was a good introduction to converting between binary and decimal. But unfortunately, binary and decimal are not the only number systems you will run into when working with computers. If you're already comfortable with binary, octal, decimal, and hexadecimal systems, please feel free to skip the last 5 minutes of this video. In binary, base 2, each digit can have 2 possible values, 0 or 1. We'll skip over base 4 since it's unlikely you'll run into that, but the same principles apply anyway. Octal is base 8. It's less common than binary, but you'll see it from time to time. Octal can take on 8 possible values ranging from 0 to 7. Decimal is base 10, and it can take on 10 possible values ranging from 0 to 9. Hexadecimal, called hex for short, is base 16, and it can take on 16 possible values ranging from 0 to F. After we run out of numbers, we start using letters, so 10 through 15 are represented by A, B, C, D, E, and F, respectively. For any number system, not just these 4, the way to calculate how many different numbers can be represented by any given number of digits is simply to raise the base you're working with to the power of the number of digits available. Let's say we have 4 digits available. In binary, we raise 2, because it's base 2, to the 4th power, and we get 16 different numbers that can be represented using these 4 digits. Remembering that 0 counts as a possible number, that would give us a range of 0 to 1111, or 0 through 15. In octal, raise the base 8 to the 4th power and get 4096 possible numbers. That would give us a range of 0 to 7777. That's 0 to 4095 in decimal. In decimal, 10 raised to the 4th power is 10,000. Giving us a range of 0 to 9999. Finally, in hex, our largest number would be 16 raised to the 4th power, or 65,536 in decimal. That would give us a range of 0 to FFFF, or 0 to 65,535 in decimal. It's easy to see that using a larger base makes for a much more compact way of representing large numbers. For example, 3 digits in hex, FFF, need 12 digits in binary, giving us 1111, 1111, 1111. Computer hardware and software at the machine code level is based on binary, so staying with a number system that's a power of 2 makes it much easier to convert between these systems. 3 binary digits can translate directly into 1 octal digit, and 4 binary digits can be directly represented by a single hex digit. In decimal, you see there is not this exact digit-to-digit conversion possible. To convert from any base system to decimal, you can draw a table like the one we used previously, but substitute the right column header values for whichever base you're working with. For binary, that would be 1, 2, 4, 8, etc. For octal, that would be 1, 8, 64, 512, etc. For decimal, that would be 1, 10, 100, 1000, etc. And for hex, it would be 1, 16, 256, and 4096, etc. Notice that all of these column headers are the base raised to the power of 0, 1, 2, 3, etc. This works for any base you need to work with. I hope this helps. You may need to refer back to this section when covering the last video in this lesson, where hex is used for IPv6 addressing.
In this video, you will learn to describe the 4-octet format used by IPv4 IP addresses, describe the difference between Class A, B, C, D, and E networks.
Let's begin by talking about Internet Protocol version 4. IPv4 uses a 32-bit addressing schema that is divided into 4 octets of 8 bits each. Now you should remember from the previous video that 8 digits of base 2 ones and zeros can have values ranging from 0 to 255 in decimal notation, which is 2 raised to the 8th power. Expressed in decimal format, this gives IPv4 addresses a range from 0.0.0.0 with all bits off to 255.255.255.255 with all bits on. Since the value of any of the 4 octets can range between 0 and 255, this gives IPv4 a very large number of possible addresses. 4,294,967,296 to be exact. This seems like a very big number, but we're already getting short of IPv4 addresses. If we convert this IP address to binary, the way the computer sees it, this will be its representation. Using the same method we used in the last video, we can convert each octet from decimal to binary. For the decimal number 10, we check the 16 placeholder. 16 is greater than 10, so we put a 0 there. So the next placeholder is 8, and we can subtract 8 from 10, so that placeholder gets a 1, and we have 2 left over. You cannot subtract 4 from 2, so the 4 placeholder gets a 0. You can subtract 2 from 2, so the 2 placeholder gets a 1, and we have 0 left over. With 0 left over, we're done, so any remaining placeholders get a 0. You can see each octet contains 8 bits, which is why it is called an octet. An IP address is divided into a network portion and a host portion, which is something that you can configure on your own computer. But most of the time computers are set up now to allow DHCP, or Dynamic Host Configuration Protocol, to dynamically configure IP addresses for you. So let's take a look at this in action. By logging into our server, server 100, let's take a look at the interface IP address. My IP address is 192.168.52.3, 4 octets, and we have this /24. This whole number is called the CIDR range. The /24 defines how many bits of the IP address are dedicated to the network portion of the address. So each IPv4 address has a network portion and a host portion. The size of the host portion defines how many hosts or endpoints this network segment can hold. In this example, the network portion uses 24 bits of the 32-bit address, which leaves 8 bits for the host portion. 2 raised to the 8th power is 256, so that's the largest number of hosts that this network segment can support, 0 through 255. In the early days of IPv4, networks used the classful addressing schema, which allowed for only 5 different address ranges. Class A goes from 0.0.0.0 to 127.255.255.255. This is for special use and unicast. The default subnet mask is 255.0.0.0, which we will explore more later on. This is the Class B, the Class C, the Class D, and Class E. Use these address ranges. Class D is reserved for multicast groups, so you will see protocols like NetBIOS using addresses in this range to communicate. And finally, Class E, which is reserved for research, development, and future uses. So this is classful addressing. In Class A networks, the first octet is used for the network portion, and the last 3 octets are used for the host portion. In Class B networks, the first 2 octets are dedicated to the network, and the last 2 to the host. Class C networks have the first 3 octets dedicated to the network, and only the last octet is dedicated to the host.
In this video, you will learn to describe how the IP protocol uses IP addresses to route traffic, describe the contents of the IP protocol header, describe how network masks work and why they are necessary.
The Internet Protocol, or IP protocol, works with Layer 3 devices which use the IP header to identify and process traffic. All routers inspect the destination address of each packet, but stateful firewalls also inspect the source address so they can identify where the traffic is coming from. As we saw in the last video, IP addresses are represented by a quad dot notation, or a string of 4 numbers separated by dots. For example, 10.195.210.10. As you can see, there are 4 octets or 4 groups of 8 binary bits separated by dots. In decimal form, an 8-digit binary number can take on a value from 0 to 255, always a positive integer. In binary form, the range is expressed as 00000000 to 11111111. A routable protocol is a protocol that can be routed outside of the network it was originated in. Normally, this would be the Internet. IP is a routable protocol, but not all IP addresses are routable. For these reasons, it's very important that you're very comfortable with how IP addresses work, including the purpose of subnet masks and default gateways. So this is an example of an IP protocol header. The version of the protocol, whether it's IPv4 or IPv6, is the first thing declared in the header. This makes sense if you think about it. Since the IPv4 and IPv6 headers are different, the device doing the inspection would have to know how to interpret the header before it could make sense of it. TTL is time to live. When a packet is sent, a TTL value is set to limit the number of hops the packet can take before it's dropped. Each time the packet is inspected by a level 3 device, the TTL is decreased by 1. When it hits 0, the router will drop the packet instead of forwarding it. This is done to prevent packets with bad IP addresses from bouncing all around the Internet forever, leading to unmanageable congestion. This is an 8-bit field, so we already know that it can contain values from 0 to 255. But the Internet Standards Committee recommends the TTL be set at 64 for most normal traffic. Note that TTL is measured in hops for the IP protocol, but some protocols like DNS, it's measured in seconds. Another important field is the protocol. Each protocol has an ID. For example, ICMP or ping is protocol 1, TCP is protocol 6, and UDP has an ID of 17. Two very important fields are the source and destination IP addresses. The source IP address identifies the endpoint that is sending this packet. And obviously the destination IP address is where the packet is being sent to. And finally, payload is the content of the message that's being sent. Using Wireshark to capture a few packets, first you see the frame, then the layer 2 data. The MAC addresses are at this level. And then there's layer 3, which in this case is the Internet Protocol version 4. This is the source IP address. This is the destination IP address. The protocol is ICMP. The computer with the IP address ending in .104 is trying to ping a computer at an address that ends in .1. So now let's talk about network masks. The subnet mask is the assignment of bits to be used by the host or router to determine how the network and the subnet information is partitioned from the host information in the IP address. You remember from the last video the /24 at the end of the IP address that indicated the first 24 bits or 3 octets of that particular IP address was the network portion, leaving the last 8 bits or 1 octet for the host address? The network mask is what accomplishes this division of an IP address into a network and a host segment. This complexity is necessary because different networks are configured to use different amounts of the IP address for the network and the host. Recall the discussion of the Class A, Class B, Class C, and Class D network schemas. On the server, you see the IP address with a prefix of 24. 24 means the first 24 bits or 3 octets are for the network portion, and the last octet is for the host portion. And when we create a packet that has to go outside of our local network, it'll be sent to the default gateway. So in this case, we need to communicate with a host outside of the network. So the packet will be sent to this address. This is the router that acts as our default gateway. The gateway will forward the packet on outside of our network segment. So whenever we need to communicate with a system that's outside of our network segment, We only need to talk to our gateway and it will manage the traffic going to points outside of our network or coming in from the outside. If we need to communicate with a host that's inside of our network, any switch or hub can do that job. But instead of sending the packet to the default gateway, our system will look in the MAC table to translate the IP address to a MAC address, so the packet will be forwarded directly to the local recipient. The broadcast IP address is, in a sense, the opposite of a network mask. In this case, the broadcast IP address will have all the octets for the network portion of the original IP address, with the octets or bits for the host portion turned on or all set to 1. For this computer, the IP address is 192.168.52.3, and the broadcast address would therefore be 192.168.52.255. As you can see, all the bits of the host portion of the address are turned on.
In this video, you will learn to describe the structure of the IPv6 address schema, describe an IPv6 header, describe what is meant by unicast, multicast, and anycast in IPv6 addressing schemes.
Let's talk about IPv6. We've covered extensively in the previous videos that IPv4 addresses were 32 bits long. Remember the discussions about the address being 4 8-bit octets? Since the world is running out of IP addresses using IPv4 protocol, the latest version of the IP protocol, IPv6, extends the address length from 32 bits to 128 bits. We're going to be dealing with hex numbers now, so refer back to the first video in the lesson if you need a refresher. An IPv6 address, being 128 bits long, is 4 times longer than the 32-bit IPv4 address, but that does not give us only 4 times as many addresses. In the first video in this lesson, we learned that 2 to the 32nd power gives us just under 4.3 billion possible addresses, while 2 to the 128th power in decimal format is about 3.4 times 10 to the 28th power, which, according to Wikipedia, would be called 34 octillion. I'm getting a bit off topic again, but that's a very big number. Like the number of atoms in an elephant big. An IPv6 address is divided into 8 4-digit hexadecimal values, each separated by a colon as shown here. Each single hexadecimal digit can have 16 possible values, which makes it a 4-bit long binary. So a group of 4 hex numbers would be 16 bits. And there are 8 of these in the IPv6 address, so 8 times 16 brings us up to 128 bits. There are a few rules to remember when representing an IPv6 address. An IPv6 address is not case sensitive. You don't need to specify leading zeros in the address, and you can use a double colon to represent any number of consecutive zeros. So for example, instead of writing 0:0:0:0:0:0:1, we'll use : 1. Of course, to keep it interesting, there is one exception to this rule. You can only use the double colon replacement once in an IPv6 address. This is an example of an IPv4 header. You should remember the version, time to live, protocol, source IP address, and the destination IP address. This is an example of an IPv6 header. It actually has fewer fields. The first field, of course, is the version. Here is the source IP address, but instead of being 32 bits long, it's 128 bits long, as is the destination address. There are 3 different types of addressing schemas allowed in IPv4: unicast, broadcast, and multicast. In unicast mode, one computer communicates with just one other system. In broadcast mode, one computer communicates with all of the other systems on that same subnet. You may remember that the network portion of the broadcast address is the same as the network portion of every other computer on that subnet, but the host portion has all the bits turned on, or set to 1. This ensures that the packet will be sent to all of the endpoints on the subnet. Multicast is a one-to-many arrangement. A group of systems can subscribe to a multicast address, so anything sent by that address will be received only by the systems that are subscribed to receive multicasts from that system. In IPv6, things are a little different. Unicast and multicast are essentially the same, but broadcast has been replaced by anycast. An IPv6 anycast address is an address that's assigned to more than one interface. Typically, the address belongs to different endpoints. A packet that is sent to an anycast address is routed to the nearest interface that has that address. So, that is the basics of the IP protocol. I hope this makes sense to you and you can now see both the similarities and the differences between the IPv4 and IPv6 addressing. Thank you.
In this video, you will learn to describe the difference between the TCP and UDP transport layer protocols, list the various utilities that use the UDP protocol.
This lesson is being presented by Ben Briggs and is based upon a lecture series developed by Moises Mong. Today we're going to talk about the two major transport protocols, TCP, the Transport Control Protocol, and UDP, the User Datagram Protocol. We'll see how they differ in the services they provide. Transport protocols are sort of like the envelope that you put a letter into. The front face of the envelope is like the packet header. This is where we write the sender's address and the destination address and so forth. To extend this analogy, TCP is sort of like sending a letter using priority mail, where you get a tracking number and the signature of the receiver, so you can be sure that the letter got to its intended recipient. Well, UDP is more like using bulk mail. It's fast and cheap, and the vast majority of letters will get to their intended destination, but you never really know for sure. Some applications like to use TCP, while others like to use UDP. Some applications can be configured to use either TCP or UDP, and a few applications use both, but for different functions. TCP sets up a connection, so the sending and receiving computers know which packets have been sent and received, and which is the correct order. The assurance that no packet is lost without being resent and that all packets are in the right order is critical for many applications, but all that handshaking requires a lot of overhead, so it's not very fast. UDP, on the other hand, does not set up a connection the same way TCP does. The sender does not know if each packet has been received, and the receiver can only reassemble the data stream in the order the packets arrive, even if some are not in the order they were sent. This requires very little overhead, so it's a very fast protocol and great for streaming videos and music, where it doesn't matter much if a few packets were lost or are out of order. At layer 4, or transport layer, the data is broken into chunks, and a header is added. The source port number identifies the process that's making the call to the network, so the source port number is added to the packet header. The destination port number represents the remote service we're trying to connect to, so that will also be added to the header. In this example, the source port is 25, which means that we're trying to communicate with an STMP server, that's Simple Mail Transport Protocol. These are the fields that a UDP packetgram encapsulates. You can see the source and destination ports, which are often the same number for protocols using UDP. Then there is the UDP message length and its checksum. Common protocols that use UDP are TFTP, the Trivial File Transport Protocol, using port 69. This is very similar to FTP, but uses UDP instead of TCP to avoid all of the overhead of establishing and maintaining a connection just to transfer very small files. DNS, the Domain Name System, uses port 53. DNS uses UDP for its name queries, but it can use TCP for less common tasks. DNS is commonly used to translate domain names into IP addresses. SNMP, the Simple Network Management Protocol, uses ports 161 and 162. It is uncommon, but SNMP can also use TCP. SNMP is used to monitor and manage network devices. DHCP, the Dynamic Host Configuration Protocol, uses port 67. DHCP automatically assigns and manages a pool of IP addresses to the systems that are subscribed to it. VoIP, or Voice over IP, uses port 5060. It can also be implemented using TCP, and is used for sending voice over the internet and is growing in popularity with internet-based phone services. IPTV, or Internet Protocol Television, streams TV signals. IPTV uses both UDP and TCP, as well as ports 80, 5004, and 12,000, depending upon which service is being used and whether the traffic is inbound or outbound. All of these protocols take advantage of UDP because it's so fast, and a dropped packet here or there is not a showstopper.
In this video, you will learn to describe why TCP is inherently more reliable than UDP, describe how security is handled by UDP and TCP, describe which of these protocols is faster and why.
Going back to our traditional mail analogy for UDP, the sender puts a destination address on a letter, drops it in the mail, and that's that. The letter either arrived or it didn't. The sender will never know. TCP, on the other hand, requires an acknowledgement from the destination that the letter was received. Unlike traditional mail, TCP only waits about 3 seconds for the acknowledgement before automatically resending the packet. When a TCP connection is established, the first thing that's done is a three-way handshake. The sender, who's trying to establish the connection, sends a SYN, that's Synchronize Sequence Number, request to the recipient system. The recipient system responds with a SYN plus ACK signal. That is, the SYN plus an acknowledgement to indicate the sequence number the communication will start with. So let's take a look at a few captured packets here. In this case, we're trying to establish an SSH, or Secure Shell, connection from our system at 192.168.52.1 to the server at 192.168.52.100. Here are the first 3 packets. This is the SYN, and you can see the flags here. The SYN flag is set to 1. Each flag can take on only 2 possible values, a 0 or a 1. So in this case, the flag is on. We expect the next packet to contain the SYN ACK. We see the SYN is on, and also that the ACK is on. And the last packet just contains a simple ACK. Once the three-way handshake is successful, a TCP connection is established, and we can start transmitting data. You can see here what follows the handshake is the actual SSH information being sent from the client to the server. A quick overview of the transport layer protocols. Both UDP and TCP multiplex data using ports. This means that the data stream is broken down into small chunks of data, put into separate packets, and addressed and sent. In our traditional mail analogy, that would be like taking a long letter and putting it into envelopes 1 page at a time and mailing each separately. We know that UDP is a connectionless protocol, so it sends off its packets and does not ask or receive any acknowledgement from the destination that we hope is receiving those packets. On the other hand, TCP is a connection-oriented protocol, so the first thing it does is use the three-way handshake to establish a connection with the recipient before it starts transmitting any data. Not only that, but it receives an acknowledgement that each and every packet has been received, or it will send it again. UDP is considered unreliable because it doesn't care whether the destination received the packet or not. TCP, on the other hand, is considered reliable because it will continue to retransmit a packet until it receives an acknowledgement from the destination that the packet has been received. UDP sends datagrams in the order the transport layer gets them from the requesting application, but they are reassembled by the receiving system only in the order they are received, and only those packets that are actually received. Obviously, this works perfectly well for many applications, but not so well for others. A bundle of data and headers in UDP is known as a datagram. In TCP, that bundle is called a segment. TCP has flow control, which means the sender will not send packets faster than the receiving system can process them. UDP does not have flow control, so there's always the risk of the recipient being overwhelmed under some conditions. We saw the UDP header earlier. This is the TCP packet header. You should recognize from the packet capture we just saw features like the source port, the destination port, the SYN and ACK flags, along with a number of others. Let's take another look at the transmission control protocol on layer 4. We can see for this packet the source port is 58,038 and the destination port is 22. Port 22 is used for SSH, so this packet header tells us an attempt is being made to connect to a remote SSH server by a process using the local port 58,038. The packet header contains the sequence number and an acknowledgement number. A number of flags you can easily look up with a Google search if you want to dig a little deeper, and the checksum. Applications that use TCP include HTTP, the hypertext transport protocol that connects the World Wide Web, HTTPS, or secure HTTP, which adds encryption, SMTP, the Simple Mail Transport Protocol, and FTP, the File Transfer Protocol. As mentioned before, in TCP, the segment that is sent must be acknowledged by the destination so we can keep sending packets. In reality, TCP often sends data in a series instead of waiting for an acknowledgement for each and every packet. The receiving computer can look at the sequence number to tell if a packet is missing from a series and can let the sender know to resend only the missing packet. TCP uses sequence numbers and acknowledgement numbers. Once a packet is received, the receiving system sends an ACK or acknowledge number. That ACK number is going to be the sequence number for the next datagram segment that is sent. HTTP works in a request-response cycle. The client requests a web page and the server returns that requested page as a response. The HTTP packet is made up of 3 blocks: the start line, the header, and the body. By now, everyone aspiring to be a cybersecurity analyst should know that HTTP protocol is not at all secure. HTTPS, or secure HTTP, was developed to address the need for privacy and security on the Internet. HTTPS incorporates the use of SSL certificates so your data is encrypted and travels securely across the network. To be more precise, SSL acts as the outermost protocol layer, so nothing after its initial handshake is exposed or sent unencrypted.
Hello and welcome to Using Your Windows Lab Workspace. We're excited for you to take these next steps in your skills journey. The labs in this course and other courses provide you with a virtual, hands-on lab environment where you can boost your skills by practicing what you've learned in your course videos and readings. Your lab space, also known as a guided project or the My Cloud Workspace window, contains all the software you need to successfully complete your lab tasks. You'll also open a lab instructions file. For your best experience, we recommend displaying your lab space and instructions side by side. To access your hands-on lab, first open the item in the course for the hands-on lab. If the lab instructions display in a new tab, hover over the tab and pull the tab down onto the desktop. You can drag the window edges to resize the window to about 1/3 of the screen size. You'll return to this window later. Return to the course screen and scroll through the displayed course lab instructions. Select the checkbox to accept the Coursera Honor Code conditions. Then click the Open Tool button. Next, you'll see the Coursera Guided Project window. This window may take a moment to display. The displayed My Cloud Workspace window is divided into 2 panes. The left pane is named the Cloud Workspace window, and the right pane is named the Instructions window. You won't use this Instructions window. Now, you can expand the Cloud Workspace pane on your screen's left side using one of 2 methods. Drag the vertical slider between the Cloud Workspace and the Instructions pane to the far right side of the screen, or click the Expand Cloud Workspace window button displayed on the top right of the left pane. Take a moment to view your lab window. You can click the lab window resolution drop-down arrow to adjust the size of the on-screen icons in the Cloud Workspace. And next, let's adjust your browser windows to see your Cloud Workspace and lab instructions side by side. On the Cloud Workspace Lab window, hover over the double box icon located in the top right of the browser window to reduce the size of your window. Move the window to the left side of the screen. Now, drag the window's right edge so that the Cloud Workspace Lab window uses about 2/3 of the available desktop space. Next, select the browser window that displays your lab instructions. Drag the instructions window so that the window is to the right of the Cloud Workspace Lab window. Now, you can perform the lab tasks in the Cloud Workspace window while using the lab instructions. After completing the lab, select Leave Session to close the Cloud Workspace window, then close your lab instructions using the option available for your browser. Also, before you begin, here's some extra information you need to know. Each time you connect to these labs, Coursera creates a fresh new environment. Data or files you saved in a previous session are no longer available. To avoid losing your data, plan to complete your lab tasks in a single session. These labs are timed to provide enough time to complete lab tasks, but if you leave the lab session unattended, your lab may time out or end. Now, these setup instructions used a Chrome browser within Microsoft Windows 10. Other browsers and web browsers on Mac or Linux computers may use different navigation. You're now lab ready. Let's get started.
In this video, you will learn to describe DNS, the domain name system, and the service it provides. Describe DHCP, the Dynamic Host Configuration Protocol, and the service it provides.
This lesson is being presented by Ben Briggs and is based upon a lecture series developed by Moises Mong. Today's lesson will cover two very important application protocols: DNS, the domain name service that translates domain names into IP addresses, and DHCP, the Dynamic Host Configuration Protocol that automatically configures and manages the IP addresses on endpoints from a pool of available IP addresses. We'll begin with DNS. The DNS service is running on our local machine. The DNS service translates the domain names in URLs to IP addresses. It's as simple as that. So when you go to google.com, DNS will resolve that name to the actual address of Google's web server. When I try to ping google.com, DNS is going to get the actual IP address of this server to use in the ping request. We can see where the DNS server is hosted. In this case, it's our default gateway, 192.168.0.1, that's running the DNS service. Now let's talk about DHCP, the Dynamic Host Configuration Protocol. DHCP will allow a computer to automatically obtain an IP address whenever it connects to its local network from a pool of available IP addresses that the DHCP server has been configured to manage. The DHCP handshake will consist of 4 packets that go between the requesting system and the DHCP server. They are known as discover, offer, request, and acknowledgement messages. When an endpoint connects to a network, if it's configured for DHCP, the system will immediately try to discover the DHCP server, so it will send a broadcast message to all the endpoints on the network segment. You remember we learned about sending broadcast messages in the first week of this course. If the endpoint had an IP address from a previous boot up, it may ask in the request to be allowed to renew a lease on that address rather than be issued a new address. If there is a DHCP server on the network segment, and there should be if there are endpoints that are configured for DHCP, the DHCP server will send an offer message back to the requesting endpoint. The offer message will contain the MAC address of the requesting endpoint, the IP address that's being offered, the subnet mask, the lease duration, and the IP address of the DHCP server that's making the offer. It's very possible that a network is configured with more than one DHCP server, so the requesting endpoint might receive multiple offers. After receiving offers, the endpoint will reply with a request message that indicates which offer it's accepted. The winning DHCP server sends a final ACK or acknowledgement message to the endpoint confirming that it can have the offered IP address, and then it marks that IP address as leased to the MAC address of the endpoint. The other DHCP service will return their offered addresses to their pools of available addresses. This is a Wireshark capture of a DHCP discover packet. Initially, your computer doesn't know the IP address or the MAC address of the DHCP server, so you can see at layer 2, the requesting computer is using the broadcast MAC address, so all devices in its broadcast domain will receive the frame. Here at layer 3, we see that there's a broadcast IP address being used. And at layer 4, we see we're using boot PC, which is DHCP, which is using UDP, and is running on source port 68, destination port 67. The DHCP server will be listening on port 67. Once it receives a DHCP request, it will check its pool of IP addresses to see if one is available. If it has one to lease, it will reply back to the requesting endpoint with a DHCP offer containing the proposed IP address and related information like the DHCP server's address, the address of the default gateway, the subnet mask, and the lease duration. Even though the endpoint now knows the address of the DHCP server, it will reply to the offer it has accepted with a request message that is broadcast rather than sent directly. This is to let any other responding DHCP servers know that an offer has been accepted and they can return their offered IP addresses to their address pools. Here is the DHCP request packet. You can see it repeats the same IP data that was sent to the endpoint in the offer message. Finally, the DHCP server sends the acknowledgement message to the endpoint, confirming that it is leased at the previously sent IP address.
In this video, you will learn to describe the syslog protocol and the functions it provides, describe the 3 syslog layers, syslog content, syslog application, and syslog transport.
Now let's talk about the syslog protocol. Syslog is a standard protocol for messaging and logging. Every event on any piece of computer or network equipment generates a message that's stored in a local log file. Syslog is a protocol that provides a standard format and mechanism to forward all of these messages to a centralized syslog server where system management and system auditing can take place. General information analysis for debugging and forensic investigations could also be performed using syslog data. Syslog has 3 layers: content, application, and transport. Content is where the actual syslog message is contained. Application allows the syslog message to be routed, analyzed, and stored. And transport handles sending the syslog message across the network. With syslog, we can talk about 5 different players. The originator, that is the entity, like your local machine, where the event occurred and the original message was created. The collector, that is the syslog server that's collecting the messages. There may be a relay server that sits between the originator and the collector that merely forwards the messages on. There is the transport sender, which is usually the same as the originator, which prepares the message for transport using UDP, or if needed for high reliability, using TCP. And finally, there is the transport receiver, which is usually the same as the relay or the collector. The transport receiver takes the message from the Pacific Transport Protocol and delivers it unwrapped to the syslog server. The process that originates the message always includes the process ID and the severity level, but the syslog client adds 3 pieces of information to the message header before forwarding it to the syslog server. The client adds the originator process ID, a timestamp, and the host name or IP address of the device that originated the message. So a little more detail on facility codes. The facility code identifies the process that originated the message. Syslog was originally implemented on BSD Unix, so the facility names reflect the Berkeley software distribution process names and daemons. Syslog recognizes 23 facility codes. If you're receiving messages from a Unix system, consider using the user facility codes as your first choice. Note that facility codes 16 through 23, named Local 0 through Local 7, are not used by Unix and are traditionally used by networking equipment like Cisco routers, which use Local 6 or Local 7. The second syslog parameter to configure is the syslog severity level. There are 8 severity levels ranging from the most severe, which is severity level 0, or emergency, to the least severe level, which is 7, or debug. Computers and networking equipments can generate literally millions of log messages per minute. You do not want to flood your syslog server with millions and millions of routine messages that will make it difficult to analyze all of the incoming data and find actionable anomalies. For this reason, it's important to set the severity level on the originator so that only messages that are of that level or more severe are sent. For example, if you set the severity level to 3, all messages with severity levels 0, 1, 2, or 3 would be sent, but no messages with severity levels of 4 through 7 would be sent. This is our packet capture of a syslog message. Here's the originator, and here's the collector. This could have been a relay, but in this case it's the final collector. This identifies the facility, and over here is the severity level. Finally, the actual contents of the syslog message, including the timestamp.
In this video, you will learn to describe how flow utilities like NetFlow allow you to collect and visualize network traffic flow statistics on your routing devices.
So what type of usage data will we see in flows? NetFlow takes samples of the flows traversing an interface. If we inspect one sample record, we will see how many packets have been used in this flow, how many bytes were sent, a timestamp recording of when the flow started, when the sample was taken, the identity of the incoming and outgoing interface. We'll also see QoS, or quality of service information, like the type of service, and we will see what IP protocol was used. For example, protocol 1 is ICMP, 17 is UDP, and 6 is TCP. And of course we will see the source and destination IP addresses, as well as all the source and destination port numbers for TCP and UDP. These are charts taken from a NetFlow server. It's up to the NetFlow server to display all of the collected data in a way that can be easily understood. Once NetFlow data has been collected, it's easy to see what protocols are used most at this interface. In this case, more than 84% of the traffic is TCP or World Wide Web traffic. Remember that this data is collected and displayed for one interface at a time. It's also easy to see the traffic by the application that's using the interface. No surprise that HTTP is number 1. We can see how many bytes are ingress or coming into the interface and how many are egress or leaving the interface. And of course we can see the number of packets that are being sent across the interface in each direction.
In this video, you will learn to describe what is meant by port mirroring and how it is used. Describe promiscuous mode and its legitimate and illegitimate uses.
The last thing to cover in this lesson is port mirroring. Port mirroring, very simply, is when a switch is configured to make a copy of all the traffic traversing one or more ports on that switch and send the copied packets out to a single destination port. Port mirroring on a Cisco switch is generally referred to as Switch Port Analyzer, or SPAN. There's also Remote Switch Port Analyzer, or RSPAN, which allows the destination port to be remote, or on a switch other than the one that's doing the collecting. Different vendors use different names for port mirroring. 3Com, for example, calls it RAP, for Roving Analysis Port. The benefits of being able to make and use a copy of all network traffic crossing a switch for network analysis purposes or to debug errors on a network are obvious. But I hope by this point your instincts will tell you that this can also be very dangerous. Imagine the trouble that might result if an attacker could access a major switch within an organization and set up port mirroring to send a copy of all network traffic back to their own servers for exploitation without being detected. Most of the time, the mirrored packets will be sent to an IDS, or Intrusion Detection system, that's connected to the destination port for analysis. The IDS will be configured to monitor all the traffic in real time and send alerts if any anomalies are detected. Remember that an IDS is off to the side working on a copy of the network data only. This means that the IDS will not slow down the network, but it also means that it cannot act directly on what it's found, like block the delivery of a packet, but it can only send out an alert to raise the alarm about what it's found. The endpoint or server that's being fed the mirrored data has to have a NIC, or a network interface card, that's running in promiscuous mode, so that it can read all of the frames it's receiving. Remember that these frames all have destination MAC addresses pointing to other systems, so a NIC not in promiscuous mode would simply ignore them. Just to reiterate, for an IDS or other network analysis tool to work, it must have a NIC that's configured in promiscuous mode so it can read all of the frames that are sent to its incoming port. Otherwise, it cannot read the frames and perform its analysis. When you use a port sniffer like Wireshark, Wireshark will put your NIC in promiscuous mode for you so it can capture all of the traffic that comes across its interface. Thank you.
In this video, you will learn to describe how the addition of network device filtering distinguishes a next-generation firewall, NGFW, from a traditional firewall. Describe how NGFWs can distinguish between business applications, non-business applications, and attacks.
Hello, welcome to this lesson. My name is Fabián Alfaro. I'm part of the IBM security team. And today we're going to talk about next generation firewalls. Basically, a next generation firewall is part of the third generation of the firewall technology. We have seen how the technology has evolved from traditional firewalls to the application or deep packet inspection firewalls that we're going to describe on this lesson. The main difference between a traditional firewall and a next generation firewall is the word sessions. We're going to understand how sessions work and what is the advantage of having them um, later on this lessons. A next generation firewall, besides performing the blocking decisions or allowing or denying traffic to go through the network based on the IP address and the layer 4 or transport layer ports. Basically, the next generation firewall is able to inspect the packets further than that. And it will inspect up to the application layer to perform the blocking decisions when it's inspecting traffic. Also, the next generation firewall is able to provide other services such as intrusion prevention system or IPS. They are also able to inspect the traffic even if it's encrypted using SSL encryption, for example, SSL inspection, for example. And we're going to describe and we're going to talk about them a little bit later on this session. The main difference between a next generation firewall and a traditional firewall are the sessions. The sessions basically allow a firewall to permit the traffic, the returning traffic, if it's part of a previously established session. So for example, if I need to connect to a web server from my PC, when the packet is going from my PC to the web server, the firewall will go ahead and inspect all traffic. And it will determine if the traffic is allowed to go through the network or if it should be denied. If the traffic is allowed to go through the network and to go through the firewall, a session, a security session or a firewall session will be created and it will be stored on a session table. When the server is responding and is sending the traffic back to my computer, if the traffic is if there was a previously established session, and if this traffic is part of the session that we created, it will be automatically allowed without needing to inspect all returning traffic. That's the main difference between a next generation firewall and a traditional firewall. For traditional firewalls, we'll have to have a rule configured to allow the traffic to go from my PC to the server, and another rule configured to permit the traffic from the server to my PC, even if it's part of a previously established TCP session, for example. So that's basically the main difference. That's basically the main difference that we have between a next generation firewall and a traditional firewall.
In this video, you will learn to describe how NGFWs can inspect and block more intrusion types by inspecting more OSI layers than is possible with traditional firewalls.
As you can see here, traditional firewall inspects or uses layer 3 and layer 4 to perform the decisions, the blocking decisions. The deep packet inspection firewall is able to use up to the application layer. It's able to inspect up to the application layer. So for example, if we have a traditional firewall allowing traffic, HTTP traffic from my PC to web server, if we have another application such as, I don't know, something like Skype or on any other application that is using HTTP, like to transport the traffic, if we have a traditional firewall rule with a rule configured to allow HTTP traffic and we want to block specifically that application that is using HTTP traffic to transport the packets, we're not going to be able to do that because we cannot be that granular when configuring traditional firewall. With the next generation firewall, we are able to inspect up to the application layer. And we're going to be able to determine if the real application is HTTP or it's another application. So as you can see here, with the next generation firewall or a deep packet inspection firewall, we're going to be able to permit and block specific applications. So this is not the case, but assuming that you have, for example, applications such as Facebook and YouTube, that they both uses HTTP. If you have a traditional firewall allowing HTTP traffic, you're not going to be able to block specifically YouTube or Facebook because they will be using HTTP traffic, and we have a rule configured to allow that traffic. So the next generation firewall, we're going to inspect the traffic further than just destination transport port, which is 80 for HTTP. We're going to be able to identify the real application. So, for example, you can permit HTTP traffic, but at the same time, you can be blocking YouTube, and at the same time, you can be allowing Facebook, for example. So a next generation firewall allows you to be that granular when configuring the rules to block or to permit or block traffic.
In this video, you will learn to describe the flow of packets through a NGFW and what inspections and services are performed at each step. Identify the major NGFW vendors and how their systems differ.
This is just an example, and just to illustrate how a next generation firewall works, we're going to use our Juniper SRX 240 firewall. So assuming that our traffic is going to ingress the firewall on interface number 1 and the egress interface is going to be interface number 3, basically the way this works is that we're going to be receiving the traffic on interface number 1. Here we can configure at the interface level, we can configure traditional firewall rules that will basically inspect layer 3 and layer 4 of the OSI model. The firewall then has Flow D module, which is able to provide next generation firewall capabilities. And we're going to describe how each of these modules or each of these steps work on a different, on the same course, but a little bit later. Then after determining if the traffic is able to go through the firewall, we're gonna send it out of the egress interface, and we're gonna see how that works in this section. So assuming that our ingress interface is interface number 1, we're going to check if we have a session already established for that traffic, or if we don't have a session, we're going to be processing the packet using this module here. So the first thing that we're going to check is the screens. This is simply a protection for the most common attacks, such as denial of service attacks. After determining that this is not like classified as an attack on the screen section, we're going to basically change the destination IP address using either the static NAT rules or destination NAT rules. If we have any NAT rule that should translate the destination IP of the packet, we need to do that before doing the routing decision because we're going to use the destination IP address to do our routing decision. So when we perform the destination NAT translation, or we translate the destination IP, if there is a rule to do that, we're going to check our routing table and we're going to determine what our egress interface will be. Once we have that, we now know the ingress interface, which is number 1, and the egress interface, which is number 3 in this case. On a next generation firewall, and specifically on this Juniper, each interface should be on a security zone. So assuming that interface number 1 is on the zone trust, and interface number 3 is on the zone on trust, we now have our ingress and egress zone, and that's going to be used when checking our security policies. The security policies will have a context, and the context could be from zone trust to zone on trust, for example. So once we have our zones, ingress and egress, and we know what policy rules should be processing the traffic, we're going to determine if the traffic is able to go through the firewall or not, because the policy will basically have the matching conditions and the actions to be taken on that packet. So for example, it'll say if the packet is coming from zone trust to zone on trust, from source IP 1.1.1 to destination IP 2.2.2, then the firewall will permit the traffic or will block the traffic. Assuming that our traffic is permitted and is able to go through the firewall, we're going to translate our source NAT using either a static NAT or a source NAT rule if there is a rule to do that. But assuming that we're not translating any source IP, we're going to inspect additional services that our next generation firewall is able to provide. And those additional services could be app ID to identify the real applications such as Facebook, Skype, for example, YouTube. We will have IDP, which is Intrusion Detection Prevention. Basically, it'll be analyzing the traffic against signature to be able to find virus or other threats. And we will have additional services here. If the firewall is configured to provide any of those services, it will be done here on the services section. Once everything is ready and the packet is set to be sent, then we're going to create a session, and we're gonna write our session on a session table. When the returning traffic coming from interface or the response from the server to my PC, it's coming from interface 3 as my ingress interface and 1 as my egress interface, the next generation firewall will be able to understand that this is part of an existing session. And all this processing is not going to be done because it knows that it's part of a response. That's the main difference between a next generation firewall and traditional firewall. As I mentioned, some of the comparisons against the next generation between a next generation firewall and a traditional firewall is that they're able to inspect up to the application layer. They're able to provide further services, and they are also able to be more granular when making the blocking decisions. Some examples of next generation firewalls: we have the Cisco ASA devices, we have the Palo Alto Networks, Juniper Networks, SRX, which is the one we illustrated before. And we have other vendors such as McAfee, Meraki, for example, Barracuda, SonicWall, FortiGates, Checkpoints, and WatchGuards. And we also have some options here. If we want to use an open source next generation firewall, we can configure pfSense, for example, and we have some other options such as the ClearOS and the IPCOP, for example, which is an open source Linux firewall.
In this video, you will learn to describe how intrusion detection systems, IDS, work. Describe what differentiates an intrusion prevention system, IPS, from an IDS.
Now, on the services section, we talked a little bit about intrusion detection prevention. And right now, we're going to see the difference between an intrusion detection system and an intrusion prevention system. An intrusion detection system is basically a device that is able to analyze the content of each packet up to the application layer. It basically compares the traffic against predefined database of signatures to determine network threats or viruses, for example, and detect those threats. The IDS or intrusion detection system is only able to detect that traffic and will send us an alert when a virus is found or something like that. The difference, or we have actually two different types of IDS. We have signature based and anomaly based. The signature based, as I mentioned, is able to compare the contents of the packet against set of predefined signatures, and anomaly based basically monitors the network traffic. It actually has a baseline of our network traffic. If it sees a deviation of our baseline, it will alert the administrator that something is going on or there's something anomalous there, so it can be inspected. But again, it's only detecting so far. The IDS could be host based or could be network based. It could be installed on a end host, or it could be on the network, analyzing network traffic. Just as an example, we have the IBM Real Secure Server Sensor and Cisco IDS 4200 series. Those are examples of network intrusion detection system. So where are we going to have our IDS system? Basically, the requirements for us to be able to have an IDS is that we need to have a spam port on the switch, which is basically a port that will be used to send a copy of the traffic. So for example, I can configure my switch to send me a copy of all traffic going through the switch, like here, through the interface or to the interface number 2. So everything that is going through the switch will be copied and sent over to port number 2, where my network-based IDS system is located. Hybrid IDS implementation simply is a deployment where I'm able to combine a host intrusion detection system and a network-based intrusion detection system. And we finally have the intrusion prevention system, which this is not only able to detect network threats, it will only able to prevent that traffic from going in. So basically, we have on an intrusion prevention system, we have an inline device. I mean, this device will take decisions. It will allow or deny traffic to go through the network. It's not going to only detect us, but it's able to prevent that traffic from going through the network. That's the main difference. And we're going to see later on this section that basically with an IPS, we're able to not only detect traffic, but we're also able to prevent that traffic. How do we do that? We basically use the same detection technologies. We can use signature-based or anomaly-based. So for example, in a signature-based detection, we inspect all traffic, all the contents of the packet against a predefined database of signatures. If our contents match an entry on our signature database, basically the IPS will be able to block that traffic. It won't be allowing that traffic to go through the firewall or through the IPS. And in a statistical anomaly detection, it's basically the same that we talked with the IDS devices. Basically, we are able to configure a baseline or establish a baseline. And if the IPS determines that there is a deviation on that baseline, it will go ahead and not only detect and report that anomaly, but it can also block the traffic that is deviating from the baseline. And that's basically what a next generation firewall is, what intrusion prevention system is, and what an intrusion detection system is. Thank you so much for taking the time.
In this video, you will learn to describe what is meant by high availability in information technology and how it can be achieved through clustering. Describe the importance of redundancy, monitoring, and failover in achieving a highly available system. Describe the principle of NIC teaming and how to achieve high availability on next-generation firewalls.
Hello, thank you for being in this. Today we're going to talk about high availability in clustering, specifically on a next generation firewall. Basically, the information security basis should be that our information is confidential and it remains confidential for us. In other words, this means that the information should not be readable or viewed by other people that is not authorized to do that. The other important point of information security is the integrity, which is basically that the information should not be manipulated in unauthorized ways. And the third point, which is one of the most important points of information security, is the availability. And this means that our information should always be available. If we need to access our information, it should be ready to be accessible and it should be ready for us to use it. That's basically where the need of HA and clustering appear. Basically, in order for us to always have the information available, we have deployed several technologies such as high availability and chassis cluster. High availability is basically a system or a component that is continuously operational 100% of the time. Basically, if we have, for example, a next generation firewall that it's processing traffic and it's or a router that it's processing traffic and it's forwarding traffic back and forth, basically we will have two devices working together. They could be working together, or we can have an active device and a standby device. And in case the primary or the active device goes down, the secondary device or the standby device will take over and will basically continue forwarding traffic or blocking and allowing traffic if it's a next generation firewall. That's the key of high availability. The most important thing for us is that our data, our network should always be up and running. Our data should always be accessible. So that's basically the main reason why a chassis cluster and high availability appeared on the market. Basically, the requirements, if we're going to create a chassis cluster, is that the host in the virtual server, if we have, for example, a chassis cluster or two servers or more servers working together, they should be able to access the same shared storage. They should have identical network configurations, for example. Their DNS should be configured properly on both devices. If it's not set correctly, you won't be able to configure HA settings at all. They should have the same operating system version. In some technologies, such as chassis cluster, for example, when talking about next generation firewalls, sometimes they should have the same hardware and the same software level. And usually you should have a connection between them. You should have a connection between the primary and the secondary node. So how high availability works. To create a highly available system or an HA device, three characteristics should be present. You should have them in mind. The first one is redundancy and also monitoring and failover. Redundancy basically means that multiple components that you have multiple components that can do the same thing. So for example, I mentioned before that you can have, for example, an active device and a secondary device. And if the active device goes down, the secondary could take over. That's redundancy. You don't have a single point of failure. And monitoring and failover, it's basically that your secondary device, for example, should always be monitoring your primary device. Because if your active device goes down, it should be able to take over. It should be able to identify that the primary device is no longer working and should be able to take the role of the primary device. And the failover is simply when you take the primary role from the active. I mean, if the active device goes down, there will be a failover to have your secondary device working as the primary. Here, we're just including an image so you can see basically how high availability works. You have, for example, the internet, and then you have two different paths to go to your servers. If one path goes down, you should be able to use an alternate path. And at the end, you can even have RAID technology, so you can have a copy of your data on more than one disk. So if one hard disk fails, you have the data on another hard drive, for example. But we're not going to talk about RAID technology on this lesson. NIC teaming is basically technology that allows me to have more than one NIC operating at the same time. So in this way, you eliminate a single point of failure risk. So with NIC teaming, you can have two NICs working at the same time, and in this way, if one network adapter goes down or if it fails, you still have a second network adapter working. And here we can see an example of chassis cluster of a next generation firewall. In this case, we can see that we have SRX devices here, and we have an active or a primary device and a secondary device. The primary device has connections against the secondary device. And basically, we have a fabric link and a control link. The control link will be able to synchronize configuration data and some other important data for the secondary to be up to date. So for example, if the primary device, if you have a device that is connecting to the internet, your primary device will probably create a session if it allows the traffic to go through. Once that session is created, it will be synchronized using the control link against the secondary device. So in the case your secondary device needs to take over the primary role, it should have a session table which is or is the same than the one you had on the primary device. And the fabric control link is just able to forward traffic when you have an active-active scenario. I will explain what an active-active versus an active-passive HA deployment is a little bit later. Basically, in this case, you can have interface gigabit 001 and interface gigabit 301 on your secondary device connected to two switches, or it could even be the same switch. So basically, those interfaces are going to work together as a single interface. You will have a RIP interface. That's your virtual interface. If your primary interface, which is GE001, fails, your secondary interface, which is GE301, could still forward that traffic. However, each RIP interface, you have to assign it to a redundancy group. So for example, let's say that you have a redundancy group 1 here in RIP 10. So if your primary interface, which is gigabit 001, goes down, your redundancy group 1 will fail over to the secondary, and the secondary could then use gigabit 301 to forward that traffic. That's basically how it works, and that's basically the monitoring that we talked before, that the secondary device should be able to monitor the status of the primary device for it to take over the primary role. And basically here on the on-trust zone, we have the same concept. We have another RIP interface assigned probably to a different redundancy group, and two interfaces working together as a virtual interface, which is RIP 00. So this is an example of how an HA or high availability setup will be working on a next generation firewall. And this is all for this lesson. Thank you so much for attending.